Although our film is called a photodiode, we will begin our experiments with this red LED. Right now it has a voltage of 2.1 volts applied to it, and it is glowing brightly. Electricity is being converted into light. Now let's run the process in the opposite direction. We'll turn off the power and shine a bright flashlight on the LED. Now light is being converted into electricity. The LED produces a voltage of 1.6 volts. It works like a solar cell. And this mode of operation is called the photogalvanic mode. A light-emitting diode, like any diode, consists of a p-type semiconductor, in which the mobile charge carriers are positively charged holes, fused together with an n-type semiconductor, in which the mobile charge carriers are negatively charged electrons. When a forward voltage is applied to the LED, both the electrons and holes move toward the p-n junction, and when they recombine, each electron-hole pair generates a photon, the wavelength of which is determined by the energy released during recombination. When operating in photogalvanic mode, the process goes in the opposite direction. An absorbed photon generates an electron-hole pair. Electrons accumulate on one side of the p-n junction, and holes on the other, resulting in a potential difference, which we observed in our experiment. Let's conduct another experiment with a red LED. We'll disconnect the power and illuminate it with a flashlight. The multimeter shows a voltage of 1.6 volts. Let's block the flashlight beam with a red filter. Now the LED is illuminated only by red light and produces a voltage of 1.5 volts. With a green filter, the voltage remains the same. But with a blue filter, the voltage drops to 0.45 volts. Let's replace the red LED with a green one. Under the flashlight, it produces a voltage of 2.1 volts. But with the red filter, the voltage drops almost to 0. The energy of the red photons isn't enough to create electron-hole pairs. With the green filter, the voltage is 0.6 volts. And with the blue filter, it's 2.05 volts. Finally, let's put a blue LED into our setup. Under the flashlight, it produces a voltage of 2.2 volts. With the red filter, the voltage drops to 0. With the green filter, it also drops to 0. But with the blue filter, the voltage is 1.45 volts. This means that electron-hole pairs in the blue LED are created only by energetic short-wavelength blue photons. Now let's consider the photodiode connection mode, for which we need a real photodiode. We connected it in series with a 330 kilo-ohm resistor. Let's apply a voltage of 15 volts to this circuit, in the reverse direction for the photodiode. Right now the resistance of the photodiode is much greater than that of the resistor, and it is locked, so almost all the voltage drops across the photodiode, and the voltage across the resistor is close to 0. In the dark, the voltage across the resistor drops to 0 altogether. Now let's shine a flashlight on the photodiode. Now the resistance of the photodiode is low compared to the resistance of the resistor, and almost all the voltage from the source drops across the resistor. Additionally, the EMF generated by the photodiode itself is added, so the voltage across the resistor turns out to be 15.7 volts. Thus, the photodiode acts as a switch that, under the influence of light, turns the voltage on the resistor on and off.